Okay, so let's look at some facts about regular Markov chains. First of all, so we're going to assume that P is the transition matrix of a regular Markov chain. Then the following are true. First of all, there is a unique stationary matrix S, and we can find it by solving S times P is equal to S, and we'll go through some examples of that. Second of all, for any initial state S0, the SKs, which are S0 times P to the K, approach S as K goes off to infinity. So the larger K gets, excuse me, that should be an exponent K. So the larger that K gets, the closer and closer the entries of SK get to S. And finally, we also have that the matrices PK themselves approach some matrix P bar, which we call a limiting matrix. And in fact, P bar has rows. All of its rows are equal to S. All of the rows look just like S. Okay. So let's look at a completely abstract example. Let's look at the case where we have the transition matrix 0.9, 0.1, 0.4, and 0.6. Now, we would like to solve S times P is equal to S. So I'm going to let S be equal to S1, S2. Those are just what I'm calling the entries. And so then I'm looking to solve S1, S2 times this matrix 0.9, 0.1, 0.4, 0.6 is equal to the same matrix S, S1, S2. And when I multiply things through, I get the matrix S1 times 0.9 plus S2 times 0.4 as the first entry, this row times this column. And the second entry is S1 times 0.1 plus S2 times 0.6. And this is equal to S1, S2. Okay, now for two matrices to be equal to each other, they have to have equal entries. So that means that from the below, I can get that I'm looking to solve the linear system 0.9 S1 plus 0.4 S2 is equal to S1, and 0.1 S1 plus 0.6 S2 is equal to S2. Now let me make the right-hand sides of each of these zeros. So I'm going to subtract S1 from both sides on the first guy, and S2 from both sides on the second guy. So what I get on top is negative 0.1 S1 plus 0.4 S2 is equal to 0. And 0.1 S1 minus 0.4 S2 is equal to 0. Now, it doesn't really take much looking to say, hey, these two equations are dependent. I mean, the top is just the bottom multiplied by negative 1. So, hey, how are we going to solve this uniquely for values of S1 and S2? Well, we're forgetting something. We also have to remember that since S is a state matrix, that implies that S1 plus S2 has to be equal to 1. So we also have to include this condition right here when we're trying to solve for the stationary matrix. Okay, good. So I only need one of the dependent guys, so let's just stick with the very first guy. So what we're left with is the system negative 0.1 S1 plus 0.9 S2 is equal to 0, and also S1 plus S2 is equal to 1. Now, what method do we want to use to solve this? You could use substitution, and that might be your first instinct, but I think that using elimination is going to be good here. I'm going to multiply the top by 10. Why? Because that'll give me negative 1 here, which will cancel out with the 1 here. So what I'm left with is S1 plus 9S2 is equal to 0. Negative S1 plus 9S2 is equal to 0. And S1 plus S2 is equal to 1. So adding these guys together, I get that 10 S2. Oh, excuse me, I messed up here. This should have been a 4. So this right here should also be a 4. So what I'm left with is that when I add these together, we have 5S2 is equal to 1, or S2 is equal to 1/5, which is equal to 0.2. Great. Now since S1 plus S2 is equal to 1 and S2 is equal to 0.2, this implies that S1 has got to equal 0.8. So this implies that our stationary matrix S is 0.8, comma 0.2. I don't really need that comma there, sorry about that. And it's always just a good idea to check that indeed this is correct. So our matrix S times our matrix, what was it? 0.9, 0.1, 0.4, 0.6. Let's multiply these and make sure that we get the same guy back. So 0.8 times 0.8 times 0.9 is equal to 0.72. 0.2 times 0.4 is equal to 0.08. 0.8 times 0.01 is 0.08, and 0.2 times 0.6 is 0.12, and adding those together I get 0.8 and 0.2. So this really means that for any state, any initial state, if we multiply it by p enough, we eventually get down to the distribution 0.8, 0.2. No matter where we start, eventually 80% of people are in state 1, 20% of people are in state 2. Okay. Now let's just choose, randomly, let's choose a random initial guy, which is 0.5, 0.5. And let's just look at the behavior of sk is equal to s0 times p to the k. Let's just see what happens here. So again, I'm taking down my calculator, and P is going to be our matrix 0.9, 0.1, and 0.4, coming 0.6. And S is going to be our initial state matrix, which will be 0.5, 0.5. So what is S times P? That. What happens when we multiply by P squared? We get that. P cubed, P to the fourth, P to the fifth, P to the sixth, P to the seventh, P to the eighth, P to the ninth, P to the 10th, P to the 11th, P to the 12th, P to the 13th, P to the 14th, P to the 15th. Look, and by the time we get to P to the 15th, this is S15, we have basically 0.8 and 0.2. Now let's see if we raise it one more time. There we go, 0.8 and 0.2. So indeed, starting with 0.5, 0.5, eventually our state space ends up, or state matrix ends up at 0.2, 0.8. Let's also just look at the powers of P themselves. Here's P squared, here's P cubed, P to the fourth. Let me write this a special way. That's P to the fifth, P to the sixth, P to the seventh, P to the eighth, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So after 18, we get down to 0.8, 0.2, 0.8, 0.2. Notice that this row is exactly S. This row is exactly S, the stationary matrix. So indeed, we see that SK approaches S, which is 0.8, 0.2. We also see that P to the K approaches this P bar, which is the 2 by 2 matrix, whose rows are both just the stationary matrix S. So 0.8, 0.2, 0.8, 0.2. Okay, cool. Now let's look at the Verizon example again. And let's actually go through the work of finding the stationary matrix. So let's find the stationary matrix for the Verizon case where P was equal to 0.9, 0.1, 0.05, and 0.95. Right. So, in S again, we're going to let be S1, S2, and we're looking for S times P is equal to S. Now S times P is equal to S1 times 0.9, so that's 0.9 S1 plus 0.05 S2. And the second entry is 0.1 S1 plus 0.95 S2. That's equal to S1 S2. Now, you don't really have to set up the multiplication here. If you just remember that S1 represents those who are Verizon customers and S2 is those who are not, 0.9 or 90% of Verizon customers and 5% of other customers become Verizon customers. Whereas 1% of Verizon customers and 95% of other customers become other customers. So you don't really have to set up the multiplication if you just remember what means what. Okay, so this gives us two equations, which is, well, remember, three equations. 0.9 S1 plus 0.05 S2 is equal to S1. 0.1 S1 plus 0.95 S2 is equal to S2, and S1 plus S2 is equal to 1. Now, remember that these two guys happen to be dependent, so we really only needed one of them. And in fact, why don't I keep I'll just keep the first guy and get rid of this. And so I'm going to subtract S1 from both sides of the first guy, and I'm left with negative 0.1 S1 plus 0.05 S2 is equal to 0, and S1 plus S2 is equal to 1. Now I'm going to multiply the top by 10 again, because we saw last time that this left us with something nice looking. So negative S1 plus 0.5 S2 is equal to 0, and S1 plus S2 is equal to 1. And then we're going to add these together. And what that leaves us with is 0.5 plus 1 S2, so that's 1.5 S2 is equal to 1. Now 1.5 is the same thing as 3 halves, S2 is equal to 1, so multiplying both sides by 2/3, I obtain that 2/3 times 3 halves is 1. So I get S2 is equal to 2/3, and that implies that S1 is equal to 1/3, and that gives us the stationary matrix. This is precisely what I claimed it was before. We only verified it by multiplying, but this time we actually proved it. S is equal to 1/3, 2/3. So eventually, Verizon only has 1/3 of the market share, and everybody else has 2/3 of the market share, no matter where we start off. No matter what situation you start off with, eventually this is what the outcome will be, assuming that that the transition matrix stays the same. Let's look at one final example, and I'm going to look at sort of demographics of the United States. And here I'm going to let U stand for urban, S stand for suburban, and R stand for rural. And now I just completely made these numbers up. But let's imagine that people in the US move amongst these zones as follows. So here's urban, here's suburban, and here is going to be every year. And here's rural. So let's suppose that 10% every year, 10% of people who live in an urban zone move to a suburban zone. So that's going to be 0.1. And no significant number of people from an urban zone move to a rural zone. So we're just going to say that the other 90% of people in an urban zone stay there. And when it comes to suburban people, 20% of them move to cities. So that's going to be, or to urban zones, so that's 0.2. And 10% move to rural zones. So that's 0.1. And that leaves 70% of suburbanites staying in suburbia. Finally, let's say that in rural zones, we've got 0.3, 30% of the rural population is moving to urban zones. 10% of the rural population is moving to suburbs, and that leaves 60% of the rural areas to stay in rural people, to stay in the rural area. Okay, so this is our diagram. What is our matrix P? Let's see if I can fit it into here. Okay, so I need urban, suburban, rural, urban, suburban, rural. Okay. So urban to urban is 0.9, urban to suburban is 0.1, and urban to rural is 0. Suburban to urban is 0.2. Suburban to suburban is 0.7, and suburban to rural is 0.1. Finally, rural to urban is 0.3, rural to suburban is 0.1, and rural to rural is 0.6. So this is what our matrix P looks like. Now we're going to try to solve and figure out, okay, what is the stationary matrix? And the stationary matrix, again, is going to represent sort of what the end behavior of the demographic shifts are going to be. What portion of people are going to live in urban zones, suburban zones, and rural zones. So let's check this out. This time it's going to be a little bit more involved than the last one because we've got a bigger matrix going on. I'm never going to have us do anything that's way too many matrices though, so don't worry. Or way too big a matrix. Okay, so we're trying to solve S, which is S1, S2, S3, times P is equal to S1, S2, S3. Now, I'll let you do the multiplication yourself, but the first one gives, row times column gives 90% of urbanites plus 20% of suburbanites plus 30% of rural people move to the city or stay in the city. The second, the first row times, or this row times the second column gives me 1% of urbanites plus 70% of suburbanites plus 1% of ruralites move to the suburbs. And finally, the last row gives me that no urbanites move to the rural, or basically, a trace number of urbanites move to the rural lands. 1% of suburbanites, 0.1 S2, move to rural areas, and 60% of those in rural areas stay there. Finally, we're going to find that these three guys up here actually happen to be dependent. So it is always important that we keep the last condition that S1 plus S2 plus S3 is equal to 1. Okay. So let's clear this. Let's actually do this using, let's do this by using, actually doing matrix operations. But the first thing that I want to do here is I want to subtract S1, S2, and S3 from both sides of row 1, row 2, and row 3, respectively. So that means I want to subtract S1 from both sides here. That'll give me a 0 here, and that'll give me negative 0.1 here. Let me write this in red. So this is now 0, and this is negative 0.1. If I subtract S2 from both sides here, I get a 0, and I get negative 0.3. If I subtract S3 from both sides here, I get 0 and negative 0.4. So when I clean this all up and put it into matrix form, what I am left with is the following. The top becomes negative 0.1, 0.2, and 0.3. On the right, I've got 0. The next is 0.1, 0.7, and 0.1. Excuse me, this should have been a negative 0.3. And that's 0. And the last is 0, 0.1, and negative 0.4, 0, and finally 1, 1, 1, 1. Great, so this is what I'm looking to solve, and I'm going to reduce it. The first thing I'm going to do probably is take this row and put it up here. So that's going to leave me with, in fact, let me just Okay. This is going to be some work. I'm going to write it smaller. So 1, 1, 1, 1. My second row is 0 0.1, and negative 0 0.3, 0 0.1 and 0, 0, 0 0.1, negative 0 0.4, 0, and finally negative 0 0.1, 0 0.2, 0 0.3, and 0. Now, these last three rows are annoying because they've got decimals. So let me just multiply the bottom 3 by 10. What is that going to accomplish for me? I won't have to deal with decimals anymore. That's what that's going to accomplish for me. And I like that. And that's a valid row operation. We know we can do that. So across the top I have 1, 1, 1, 1. The next row becomes 1, negative 3, 1, 0. The next row is 0, 1, negative 9. No, that's a negative 4. 0, and the last one is negative 1, 2, 3, 0. Okay. Now I will subtract row 1 from row 2. And I'll just add row 1 to row 4. And what this gives me is 1, 1, 1, 1. 1 minus 1 is 0. Negative 3 minus 1 is negative 4. 1 minus 1 is 0. And 0 minus 1 is negative 1. Row 3 stays the same. And row 4 becomes 1 plus negative 1 is 0, 1 plus 2 is 3, 1 plus 3 is 4, and 1 plus 0 is 1. Now let me swap rows 2 and 3 so I can get a 1 at the next spot right there. So I get 1, 1, 1, 1. And I have 0, 1, negative 4, 0, and 0, negative 4, 0, negative 1, and 0, 3, 4, 1. Now I'm going to add 4 row 2 to row 3. I'm going to subtract 3 row 2 from row 4, and what that leaves me with is, and again, pause this and make sure that this all works out, but 1, 1, 1, 1, 0, 1. I should also have subtracted row 2 from row 1. So what does that give me upstairs? I get a 0 here, and 1 minus negative 4 is 5, and 1 minus 0 is 1. This row becomes 0, 0. Negative 4 times 4 plus 0 is negative 16, and 0 plus that is negative 1. And here, negative 3 plus 3 is 0. This is supposed to be 4. And negative 3 times negative 4 is 12, plus 4 is 16, and 0 plus 1 is 1. Okay. Now notice that these two guys down here are dependent. They're basically the same. If I add row 3 to row 4, that just cancels out row 4. So what that leaves me with is 1, 0, 5, 1, 0, 1, negative 4, 0, 0, 0, negative 16, negative 1, and 0, 0, 0, 0. Great. In fact, I like having this row of zeros down here because that tells me that I'm not going to have too many equations for too few variables. This suggests that things will actually work out. So now I'm going to divide this row by negative 16, which leaves me with 1, 0, 5. I'm going to stop writing this guy. 1, 0, 1, negative 4, 0, and 0, 0, 1, 1/16. Finally, I've got to take this guy and get rid of these numbers here. I'm going to take 4 times row 4 and add that to row 3 and add that to row 2. And I'm going to take -5 row 3 and add that to row 1. And that leaves me with, and this should give us the final answer right here, because we'll get to reduced row, or reduced form, which is what we've been trying to get to. This gives us 1, 0, -5 times 1 is -5 plus 5 is 0. -5 times 1 is 16th is -5 16ths. 1 is 16 16ths, so 16 minus 5 gives us 11 16ths. Over here I have 0, 1, 4 minus 4 is 0, and 4 over 16 is 1/4, plus 0, that just gives me 1/4, and then 0, 0, 1, 1/16. So this tells me that S1 is equal to 11 16ths, S2 is equal to 1/4, and S3 is equal to 1/16. And we should check, do these add up to 1 first of all? Yes, so I didn't mess up any of the math. You can check that. But what you should also check is that this is actually the stationary matrix. So I leave it to you to check that if S is 11 16ths, 1/4, and 1/16, then S times P is equal to S. The last thing I really care about here is the interpretation. What this really says is if trends continue, then 11 16ths of all people of the United States will live in an urban area, and 1/4 will live in a suburban area, and 1/16 will live in a rural area. So using information like this, doesn't matter what the initial distribution is, assuming that these trends continue, we can figure out what the long-term demographics are going to be. And in fact, this sort of analysis does get used in studies of demographics quite a bit. Okay.